Yes, sir. Recording has been started.
Okay, thank you. So good morning, good afternoon, good evening, participants across different time zone. Welcome to the webinar organized by IEEE IEEE PLS Joint Chapter Kerala. Today's topic is PWM Techniques for Dual Inverter Drives for Electric Vehicles. And the speaker for today is Dr. Rishi Menon, Power System Engineer, Tech Lead, Powersmiths International Co-op, Canada. I invite Dr. Bijana Kunju, our chapter chair, for formally introducing the speaker before our participants. Bijana Madam, over to you.
Yeah. Hope you can hear me. Is my
Yes, ma'am.
Yeah. Okay. So good evening, good day to all those who have joined for this particular webinar. We have been organizing such catchy webinars, of course, from various fields of interest, especially which involves a lot of research interest into the students of the area, global interests that can come up. So we have been looking into the PWM techniques before also, but we have got a PWM technique for the dual inverter drives from Dr. Rishi Menon. In fact, we are lucky to have you here today to discuss about the multi-level inverters for the traction cases. I'm indeed proud to introduce Dr. Rishi Menon. He is basically from our own state, Kerala. He has done his BTech from MG University and his MTech from Amrita College, Amrita Vishwabhidyapeetham, Bangalore. And he has done his PhD from Ontario Tech University, Canada. He has done his research in the same field of electric vehicles, and he has been working with DNV Electronics as research engineer, as well as in multi-level inverter drives. And he's currently working as a power system engineer at Powersmiths International Corporation. And his research interests includes same drives, EVs, as well as the PWM techniques. We look forward for a lot of inputs from Dr. Rishi, and we are indeed proud to have you here. Welcome, Dr. Rishi. We look forward to hear from you.
Thank you so much, Professor Bijana, for that kind words. I'm honored. Thank you. I'd like to thank Professor Biju and IEEE Kerala chapter for organizing this webinar. And I hope the topic and the information will be useful for most of the attendees. At the same time, I know it's Friday, so I would try to make it interesting and as much as informative I can. So shall we start? Professor Biju?
Yes,
sure, sir. We can start.
Yeah. All right. So as you know, the topic I'll be covering up here will be PWM techniques for dual inverter drives for EVs. So most of the thing here, the keywords will be multi-level inverters, PWM techniques, modulation index, and yeah, as I said, drives. So I hope like the attendees are familiar with these keywords and terminologies. So let's begin. So the starting of the presentation will be with a brief introduction, very general introduction, and offset power sharing PWM techniques, experimental validation of that particular method, and decoupled power sharing PWM technique, and the summary of the whole presentation in brief. So as the topic says, EVs, so electrified transportation. As you know, there is a plethora of research going on in this field. I mean, every researcher, every automobile industry is working on this area to improve the efficiency and utilization of electric vehicles around the world. So why is it so? Because of course it's a clean alternative to the combustible engine. And if you take about the maintenance and everything, it is cost effective. And no doubt in that it's better to the environment because it's clean, quite clean, no pollution. You can see here a generalized block diagram of electric vehicle, which has a battery and a converter which converts the DC to AC. Why? Because most of the industries or most of the electric vehicles which are being researched right now are useful or having AC motors, which can be induction motor or permanent magnet motors. That converter converts the DC to AC, and you have motor. From motor, you take the speed and the torque, and you have to convert into a transmission system, which can be utilized for the dynamics for the vehicle. So you have a transmission, then the vehicle load, of course, and all those things are connected to a controller where all the feedbacks and signals are provided, and that controls gives the required speed and torque, which is commanded by a user. So the user is, of course, the vehicle user who is driving the vehicle. So all these things are generic. So and a generic like block diagram for electric vehicle. Now, in current situation or in the existing industry situation, the power converters, whatever being used is two-level inverter. So what's two-level inverter is you have 3 half bridges and you have 6 switching devices, and the voltage what you switch is 0 to VDC. So you have only actually 2 levels, that is 0 and VDC. That's why it's named so, that is two-level inverter. So these inverters are predominantly having some drawbacks, which been already addressed in a lot of literatures, like since it is two levels, so the device stresses will be higher and the losses will be higher because you have a du over dt ratio, so that will be higher when you have higher DC voltages, and of course the EMI issues will always persist. There is a DC bus voltage limitation. You cannot go higher a particular limit because again it will increase the device stress and dV over by dt ratings. And it has torque ripple as well. So these are just generic ones. There are some more, but the most common and generic ones are these. Now, the solution for to avoid these losses or to minimize these losses, not avoid, but to minimize these losses, it's been suggested that multi-level inverters, like when you switch different DC levels, that could be a feasible solution to this two-level inverter. Now, if we are using a multi-level inverter, there are different or variety of multi-level inverters in the literature. So which one to choose, or which could be the most optimal converter topology for electric vehicular application? So requirements for that topology, it should be simple topology. It should not be a complex, it should be a simple topology. Of course, if you have a multi-level capability and if you have all the advantage of that, it should be modular and fault tolerant capability it should have. Now, you know that by increasing the number of switches and devices, everything, it increases the cost. So the topology should be economical for the usage. Else it will be hard to accept by the industry and the consumers. So it should be economical. So topologies, multi-level topologies can be divided into 2 major subsections, which are single DC source and multiple isolated DC source. So single DC source, you can see here, one is called neutral point clamped inverter, the other is flying capacitor inverter. Then you have multiple isolated DC source where you can isolate the DCs into 2 parts or multiple parts. They are cascaded inverter topology, and one of them is open end winding, which is also known as dual inverter. Sometimes it is also known as dual 2-level inverter. Basically, it is a 3-level inverter topology. So starting from the first, a neutral point clamped inverter, you can see here, of course, your number of devices have been increased, and you have, instead of 6, you have 12 devices, and you have a neutral point connected at across the DC link, and it has a inherent issue of DC link voltage balancing in each switching cycle. So you have a capacitor which is divided into 2, and you have to balance those capacitor in each switching cycle. So that could be a complex control. flying capacitor topology, you are replacing the diodes and you're keeping a capacitor, but here also you have to balance those capacitor in each switching cycle. And these capacitors can be electrolytic, so the cost of, due to cost of capacitor, the topology itself can be expensive. A standard cascaded edge bridge inverter. This is one of the modular topology, can be useful, but the problem here is you have to get 3 isolated DC sources. So one of the topology which has been derived from cascaded bridge is dual inverter, dual 2-level inverter. So what you can see here is you can see there are 2 inverters and they are feeding an induction motor or an AC motor with an open end winding. And what is open end winding? You take the stator windings, you open it, and there will be no neutral point. So you are feeding from both ends of the stator winding. And the topology is quite similar to the 2-level inverter because, yeah, on one side it is a 2-level inverter, on the other side also it's a 2-level inverter. So inverter 1, inverter 2 acts as 2-level inverter, and the principle which acts to make up multi-level topology is superposition principle. So you supply a voltage and you supply an opposite voltage. When they are superimposed, that gives you a multi-leveled output voltage. So compared to the other topologies, it is quite simple because in the market, in the industry, you have existing 2-level inverter, and it requires isolated DC source. So if you have a common major DC source, you just divide or split into 2 equal halves and provide isolated DC source. And the requirement for this only is a motor which need to be customized or which need to be open-ended. So it seems to be very general or very less complex topology in the multi-level topologies. Now, that's the advantage which I just shared. So there is no requirement of additional diodes and capacitor as compared to the single DC link multi-level inverters, that is flying capacitor and neutral point. And the absence of neutral point fluctuation is not available as in the NPC topology. Independent control of each inverters can be done. So you have 2 2-level inverters, both the 2-level inverters can be controlled together or independent control can be provided. It's a simple modular configuration with higher switching vectors redundancy. So that means I'll explain to you in the further slides about those. And economical, due to, as I mentioned, it is due to availability of conventional 2-level inverter and its auxiliary circuit. So 2-level inverters are already available. The thing you have to modify is on the load side, which is the motor. You have to get an open-ended configuration. So this was the thing about I was talking about. So this is a general 2-level. On the left side, what you see here is a general 2-level space vector. So you have 6 devices and you switch it across the vertices of the space vectors and you get a 2-level output. On the right side, you have a 3-level topology. So here you can see the hexagon has became bigger and you have multiple switching points because your triangle have increased inside. Now, how to make this using a dual 2-level inverter? So as I mentioned before, superposition principle. So you take 2 2-level inverters and you use one hexagon and keep the other hexagon on the vertices of the first one. So you keep, if you can see on the figure number A, superposing 2 2-level inverter space vector. So you keep hexagon on the vertices of the 1, 2, 3, 4, 5, all the 6 points. When you keep doing all that, you will get a 3-level space vector structure for dual 2-level inverter. And you can see the switching redundancies are higher for dual 2-level inverter because you're combining all the switching vectors of individual 2 2-level inverters. So this is the unique topology which can provide only this much of switching possibility. And to let you know that in industry or researching in this field, all the switching vectors, all the switching points are still being under research. Like what will be having effect of those particular switching vectors on the motor or on the load. Now, how to make these space vector points, or how to make these switching vectors? So there are multiple methods. Again, what you can do, you can have a lookup table or different other methods to get those switching vectors in digital logic. But the most common method which being used for digital utilization is triangle and modulating wave comparison. So it's similar to the two-level inverter what is being used. So you have a triangular wave, you have a high frequency triangular wave, and you have a modulating wave which is being compared to get the switching PWM. So, and the modulating wave, as you all know, instead of sinusoidal modulating wave, the modulating wave used is triplen harmonic injected modulating wave because it has better DC bus utilization and better harmonic results. And here you can see that to generate a three-level topology, you have to divide the triangle into two parts. So you have two-level shifted triangles, and they are phase disposed to each other. So how that logic is created, those triangles are being compared with the modulating wave. And when the modulating wave compares with the upper triangle, you will generate the switching frequency, not switching frequency, I'm sorry about that, the PWM pulses for the inverter 1, and when the modulating wave is compared with the lower triangle, it will generate the PWM pulses for the inverter 2. Inverter 1 and inverter 2, I'm talking about in terms of the inverter 1 and inverter 2. So in the future and the further slides, whenever I'm presenting, like I will be mentioning inverter 1, inverter 2, and the VDC 1, VDC 2, which is corresponding to inverter 1 and inverter 2 respectively. So this is the very basic logic for generating a multi-level output voltage using phase disposed carrier method and comparing with the triplen harmonic injected modulating wave. Now, when we use this dual topology for traction application like electric vehicle or any automotive application, you have two isolated DC sources, which is feeding two individual two-level inverter. So again, there will be a requirement for that. What is the requirement? You have to have a uniform discharge of both the isolated DC source. It couldn't be possible like one DC source is having, being more discharged, the other one is less discharged. So it cannot be possible. So you should have a uniform discharge of both the isolated DC source. It should be effectively utilized. I mean, both the DC source should be effectively utilized. In the DC link voltages. Then there should be a power flow control, and there should be power sharing also, because as I mentioned, the power which is taken from both the sources should be balanced and shared equally. And of course, the PWM technique, whatever will be implemented, should be simple to get all these requirements. So here comes the first main topic of dual inverter PWM technique, which is to get proper power sharing and proper equalization of individual DC buses, which is offset power sharing PWM technique in dual two-level inverter. So in real world, you can see that when three-phase modulating wave is compared to phase disposed triangle, they are placed exactly at the center of the carrier band. When the carrier band is divided, like you can see the carrier band ranges, that is minus 0.5 to plus 0.5. This can be done in multiple ways. It can be 0 to VDC, and midpoint can be 0.5 VDC, or it can be minus 0.5 VDC to plus 0.5 VDC, and the midpoint can be 0. So they have different types of representation to these. So here you can see that the modulating wave, when the modulation index is lower, it is placed at the center of the carrier band. And exactly same for the higher modulation index also, the modulating wave is placed exactly at the center of the carrier band. So with this, by naturally or inherently, it provides, per cycle average equal power sharing. That means whatever the portion the modulating wave is being compared to the upper carrier, that much of power being drawn from the inverter 2, and similarly the same portion is being compared to the lower triangle, so the same power is being drawn to the from the inverter 2. And if the modulation index is less than 1, because we generally say the modulation index varies from 0 to 1. So if the modulation index is less than 1, you can see that there are still some particular area left in the carrier band for further comparison. So what we can do, so in order to have or sharing, or different power drawing from each inverter, you can do a method which is called offset PWM technique, like this. So what you can do, you can offset the whole modulating wave to the upper or lower carrier band. What will happen if you shift the modulating wave on the upper carrier band? That means more power will be taken from the inverter 1. If you have shifted the offset to the lower carrier band, you will have more power taken from the inverter 2. So that brings us a capability to vary the power between the inverter 1 and inverter 2. Now, when the case of lower modulation index, that means if the speed is really half and the modulation index is less than 0.5, you can actually conveniently place the modulating wave in one of the carrier bands. That means you can shift the whole modulating wave in the upper carrier band, and you can shift the whole modulating wave in the lower carrier band. What does it mean? That means you can have a 2-level operation bilaterally. How? Because on the other side, the modulating wave, when the modulating wave is shifted to one of the triangle carriers, the other inverter will be naturally making either zero vectors. Either all the top devices will be on, or all the bottom devices will be on. This provides a start point bilaterally. So this gives you a capability of operating a 2-level operation at half the modulation index, or in other words, I can say at half the power or half the speed. When the modulation index is higher, that means when you have above 0.5, you can see the offset can be made or can be adjusted in a particular fashion. So the beauty you can see here, more power can be taken where the offset is higher, and more power taken if the offset is on the lower side, you can deliver more power from the inverter too. So inverter corresponding to carrier having larger portion of modulating waves will feed more power to the load than the other inverter. So how we should realize mathematically this point? Like you can define the modulation index, that is 2 over √3 maximum voltage divided by the VDC. And the limit of this offset which can be applied can be given by an expression which is plus minus 1 minus m over 2, and your limit of m should be between 0 to 1. And what is plus and minus? Here plus can be the positive offset, that is shifting the modulating wave on the upper carrier, and negative can be shifting the modulating wave on the lower carrier. So inferences from this particular equation can be made as the maximum value of offset that can be is plus or minus 0.5. Is it true? And if the modulation index is less than 0.5, modulating wave can be conveniently placed in one of the carrier. If the modulation index is between 0.5 to 1, any one carrier can have larger fraction of modulating wave. And if modulating 1 is 0, of course, if you substitute that in that, the offset will be 0. There will be no offset, and that is very least case when you are actually driving a vehicle in a cruising mode. All right, so here is small switching sequences when you do that offsetting in each carrier band. So the middle figures, they show the first triangular sector of the 3-level space vector, and you can see that there are 4 triangles in that sector. And when the vector is lying on that particular triangle, on the top and the bottom shows, top shows the positive offset and the bottom shows the negative offset. Similarly, when the triangle is on the second, I mean, the vector is on the second triangle, the top one is the positive offset and bottom one is negative offset, so on and so forth. So all the four triangle, the vector position has been realized for the switching sequences. So you can see that there is no overlapping between between the PWM pulses when you have this kind of technique. So now comes how it's been hardware implemented. So to realize or to have a proof of concept to this this particular technique on this particular topology, you have a two-level inverter which is feeding dual two-level open-ended induction motor, and controller, speed controller has been used, a generic V over F, which is scalar control of induction motor. And you can see here in the red highlighted box, you have the power sharing logic, where you are taking actually the comparisons are being done based on the DC limits or DC voltages of the DC sources. So the comparison is done through a PI controller, and you put the sharing limit, which I have just shown before in the prior slide, the limit, and you compare and you produce your modulating wave as a triplet harmonic injected or the wave you want, and you compare with the phase disposed upper and lower carrier band, and you generate the PWM pulses for both the inverters. And this is just a general specification of the hardware, whichever what was used. So an induction motor with 5.6 kilowatt, inverters were semicron stacks, and drivers were XKHI 22A and DSP controller with 20 megahertz clock. DC limits were kept lower just for the prototype application. It was 135 volt, and switching frequency was also lower for 3 kilohertz. So you can see here the scope results when the inverter was driving the motor at lower speed, or we can say at lower modulation index, or we can, if you take the concept of V over F, the frequency was 24 hertz. So here the motors are 60 hertz. So lower 30 hertz is considered to be low, less than 0.5 modulation index. So 24 hertz operation. You can see the first trace, this is the phase voltage. So you can see here it is more or less, or not more or less, but similar to a two-level operation. And you have on the left side, when both the inverters are switching equally, when both inverters are sharing equally, you have equal pole voltages on both the inverters. And fourth and fifth trace is showing you the DC current, and you can see that it is providing DC current equally. And the sixth trace is the phase current, which doesn't seems to be any different. Now, what if on the left hand side, I'm sorry about this mistake, so this should be B, when VDC is higher than VDC2. So in that case, you don't want to drain VDC2, so you have to take more power from VDC1. And if your speed or your modulation index is lower than the half, you can shift your modulating wave in the upper carrier band. That means you can see in here now all the pole voltages is being generated by inverter 1, but the effective phase voltage remains the same, which is a two-level inverter topology, right? And fourth and fifth trace, you can see that the inverter 2 is not providing any current, or no DC current is flowing from the inverter 2. Only inverter 1 is providing the current, and there is no variation or modification in the effective phase current too. Now, when the modulation index has been increased, or you are driving at higher speed, on the left side, you can see again it's a balanced operation. VDC1 is VDC2, so you can see here multi-level output is being provided by the dual two-level inverter topology, because as the modulation index increases, your waveform changes, and the pole voltages are similar because both the inverters are sharing the load and DC current, of course, and the phase current. But however, when the VDC1 is, this is just one of the example, we can make VDC2 also higher, but for just showing the concept, VDC1 higher than VDC2. So multi-level output voltage doesn't have any difference in the wave shape, and you can see that 2 and 3 there is a difference. So more pole voltage is being generated by inverter 1 and less pole voltage is being generated by inverter 2. I assume you understand what's pole voltage. So pole voltage is when you have the midpoint of each half bridge, voltage between the midpoint of each half bridge to the negative rail. That's the pole voltage, VAO, in other words, we can say, or VAO1, and in the other inverter it can be VAO2. And you can see more DC current is being fed from inverter 1 compared to inverter 2. Now, we have to take care of the dynamics, even we are doing a scalar control. So doing an acceleration, how it looks like. So you can see here, the motor is being accelerated from approximately very low speed to high speed. You can see when the voltages are identical on both the sides of the inverter, or when they are equal, of course, it is sharing the load and the pole voltages are equal, and identical amount of DC current is drawn for acceleration and the current on the 6 trays. But when you accelerate from 0 to high speed and the voltages are unequal, you can see pretty much for lower speeds, all the power is being fed from inverter 1. And inverter 2 will only come into action when your modulation index and speed is increasing. So you can see there is an, you can unequally, or you can do a proper power control by doing this. And here in this slide, it's showing a generic weighted total harmonic distortion, how it, or what effect it affects on the harmonics. So on the top, on the left side, you can see 24 hertz when the positive offset is applied, and on the bottom, you can see when the negative offset is applied at 24 hertz. So you can see there is no much difference on the harmonic spectrum and their subharmonics ranges. At the same time, you can, on the left side on the top, you can see when the 48 hertz positive offset is applied and the negative offset for 48 offset applied on the bottom of the right side. Yep, and just tabulated in a tabular form. So you can see the multiples of frequency, that is 12, 24, 36, 48, 54. And what's the difference when there is actually no offset and positive offset and negative offset. So you can see from the numbers here, it's quite obvious that very less variation. It's a difference of only 0.1 when you have an offset and when you do not have an offset. So you can infer that, or you can predict that there is no much problem doing so. Of course, your switching will change, so that's due to that effect, your harmonics have some variation. So, but that difference is not much. That's what I'm trying to say. Now, to realize this particular topology for a vehicular application, so you have to model vehicle and actual battery system, and to evaluate its performance, how it could behave in an actual drive performance on a drive cycle. So here a small work has been done. Instead of having an actual vehicle and actual all power devices, you can put all those things in a real-time simulator. So a real-time simulator has been used to model the inverter, vehicle, battery, vehicle load, and all transmission system. And the controller has been kept outside of the real-time simulator, and in that you have an actual vector control where you can control your torque and flux individually. So that's called field-oriented control, and that field-oriented control is used for speed control of the inverter. And the same power sharing logic, offset power sharing logic, has been applied. So this slide provides you the small description on what is being applied on that hardware in loop implementation. So it's basically called hardware in loop implementation. So you have a real-time simulator, which is used to model the battery, open-ended induction motor, and a medium-sized vehicle, and dual inverter. DSP controller has been used for power sharing and field-oriented control of the drive. A standard driving pattern used as speed and torque inputs to the drive. I mean, you have multiple standard patterns, right? I mean, you have US standard pattern, you have European standard pattern, and Japanese standard pattern. So I will just show you in the further slides what are those. And drive cycle test conducted for unequal SOCs, because whenever you talk about batteries, you're talking about SOCs, that is state of charge in the batteries. And so it has been tested for unequal SOC with and without power sharing control. And the drive cycle has been tested for unequal capacity of the battery also. That means unequal capacity is AH rating of the battery. So with and without power sharing control. So that's what I was talking about. FTP 72 drive cycle is a very common drive cycle of USA. And North America, it's a standard drive cycle where you test all your vehicular system and dynamics in simulation using this particular drive cycle. On the first trace shows the vehicle speed and the dynamics. And the second and the third trace shows the SOCs of the battery. And fourth and fifth shows the coulomb count. Coulomb count is a terminology used for batteries again, which shows how much current or how much power is being extracted from that particular battery. So you can see here on the left side, without power sharing control, when the SOCs are unequal, you can see both batteries are being discharged. Both batteries are being discharged even irrespective of the speed, and both batteries are being providing power to the load. From the fourth and the fifth trace, you can see that the coulomb count is increasing similar fashion simultaneously together. But on the left side, when you see here, the drive cycle, when the power sharing logic is applied, pretty much for the almost half of the drive cycle, you can see if you say VDC1 is greater than VDC2 and you apply this power sharing logic, one of the inverter is just being constant. It is not providing any power, or comparatively less power. So most of the power is drawn from the other inverter, which is having higher SOC due to this power sharing logic is being applied. And you can see the coulomb counts are different. That means more power is drawn from one of the inverter compared to the other. So this is a standard driving profile for North America, where we have tested it with unequal SOC. So now in the next driving profile, which is called ECE 15 drive profile, here it's been tested to compare the results for unequal capacity. That means unequal AH rating. So you can see the first trace again shows the speed of the vehicle, the 2 and 3 shows the SOC, and 4 and 5 shows the coulomb count. So when no power sharing logic is being applied, both side of the DC sources are both DC sources are being discharged, and power is taken identically from both of them. But when the power sharing is applied, you can see both of the DC sources are sharing the power, and different amount of coulomb count can be witnessed from traces 4 and 5. That means different amount of power is being drawn from both the sources. So whatever been discussed and shared with you right now is one of the PWM technique which can be utilized for power sharing in dual inverter when you have isolated DC source. There is one more method which is called decoupled power sharing PWM technique, and this method has been extensively researched in the industry as well as in the research field, taking two collinear vectors, the terminology called as two collinear vectors. So I will show you in a minute. So here you can see the basic logic behind that. And you have a reference voltage and you divide it in two equal halves, and you can use again as KD and KD minus 1, and these are divided in two equal halves, and you convert into modulating signal generator, whatever you want to use. You can have a triple and harmonic injected, you can have a discontinuous PWM as well, and the comparison logic is same because you already divided the modulating wave into two different halves, and that will generate your PWM pulses for each inverter. So that's what I just mentioned before. The type of PWM technique which can be used for this decoupled power sharing logic can be 30-degree clamp, which is also known as split clamp PWM, and 60-degree clamp, continual clamp, which is also known as continual clamp PWM, and THI, which is triple and harmonic injected PWM. And just to let you know, the 60-degree clamp or the continuous clamp PWM has been already patented by some of the automobile industries in North America. So as I mentioned, it's been extensively researched and maybe implemented in few years, hopefully. So just to give a brief of what is a split clamp and continuous clamp, you can see here the split clamp is 30-degree clamp, where you have a 30-degree clamp over to the DC bus on the positive and negative DC rail, and 60-degree clamp is you have a 60-degree clamping of the modulating wave on the positive and the negative DC bus rail. So comparison between both the sharing methods can be seen here. You have offset power sharing on the top and the decoupled power sharing on the bottom. Here, what you're doing, you're providing an offset for the same modulating wave, and you are using an opposite comparison logic. In the decoupled power sharing method, you are splitting the modulating wave into two equal halves, and you have your modulating signal generator, and you're comparing with the same logic. And the limits of, of course, offset has one limit. So according to, similarly, the decouple also will have a limit, like how much you can divide the gain. So the KC here, which is the offset limit, can be provided as 1 minus m over 2, where m is between 0 to 1, and the KD here gain can be 1 minus m divided by 2m, and of course it should be between 0 to 1. So I have just shown you a sinusoidal modulating wave instead of triple and harmonic, just to show how what in real world the decoupled power sharing look like. So on the left side, on top and bottom, you can see the red modulating wave and the blue modulating wave, which are the modulating wave of two inverters. So you can see when the KD is 0.5, that means the modulating waves are equally divided, which have equal sharing in the triangular waves, and it will provide equal power sharing. It will be sharing the power equally from both the DC sources. When the KD is made higher or lower, in this case, I have shown like KD is higher. So you can see the modulating wave of one of the inverter is bigger compared to the other. So here also, you have a power sharing concept or power sharing facility. So to compare this now with a how we can compare. So basically, you know that for two level or at lower speeds, at lower modulation index, both these power sharing logics will behave more or less similarly, because you have basically a two-level operation and you have two-level output voltage. The difference lies when you have a multi-level operation. So here you can see that it's a scope result. So you can see the acronyms which I have been used, like DSC is called decoupled split clamp. DCC means decoupled continual clamp, that is 60-degree clamp, and DTHI means decoupled triple harmonic injected modulating wave, and the OTHI means offset sharing logic being applied to triple and harmonic injected modulating wave. The offset sharing method. So A, B, C are the decoupled is the offset power sharing logic. So you can see there is considerable amount of change in multi-level output waveform, which could have some effect, and you can see some ripples in the A and B on the decoupled split clamp and decoupled continual clamp, which can affect the performance of the drive as a whole. But you can see the offset power sharing is more lenient and more smooth compared to the other all waveforms. So before I go to summary, I just want to show you a quick animated video which can be presented. I mean, is it? Can you see the presentation? Can anybody give me a feedback?
No, the presentation is not visible yet.
Okay.
Could you please reshare them? Same.
Yeah. I'm doing that. Screen share. Is it
Yeah.
okay now?
Yes.
Okay. So let me do this. So you can see here in this when the it's just an animation just to visually show what happens. So you have batteries here, you have two inverters feeding the motor, and when the modulating wave is exactly at the center and lower modulation index, your batteries are being balanced. And if I resume, and this is the two-level output voltage where it will be provided. So for example, now the battery 1 has gone lower, so the offset has been shifted to downwards, and battery 2 will be more providing power. At the same time, you can charge your battery 1, so it get balanced again. And when the battery 2 is lower, the offset is applied on the top, upper carrier band, and at the same time the battery 2 can be charged, and it can equalize both the batteries and have a good performance. For higher modulation index, you can see the modulating wave is higher, both are balanced, equally sharing the load. And you can see the multi-level output waveform on the side scope. When the battery 1 is low, you can see here more power is being fed from the battery 2 compared to battery 1. And again, of course, when you feed more from 2, it will also get discharged. Now the battery 2 is also lower, battery 1 will be feeding more power, but I mean, eventually they get balanced. So this was the induction motor and the inverter stack, which I mentioned before. The standard two-level inverter, then another two-level inverter, which is feeding the open-ended configuration of that particular motor. Induction motor has been used. And you can see the scope results trying to accelerate from low speed to higher speed. You can see here the waveform is being changed slowly by slowly, and you see it is going to a multi-level operation. All right, so let me go back to my presentation. So what we can summarize from this is dual two-level inverter can be a feasible solution of multi-level topology for electric vehicle application. And the power sharing PWM can do an instantaneous SOC balancing or power flow control when isolated DC sources are having different charge and capacity. Let me tell you what could cause different charge or different voltage level, because the batteries cannot stay identical. They due to dynamics or due to aging and manufacturing tolerances, they can, one of the side, the batteries can discharge faster. So to avoid that, when using this kind of topology, we should have a sharing technology, or should have a sharing technique to avoid such circumstances. And you have obviously noted that we can do a two-level operation at half the rated speed or half the power by either offset by doing a complete offset to one of the carrier band, or with decoupled method also you can actually split equally or less than 0.5 to shift the power between the inverters. So this could be a fault tolerant operation. For example, if one of the inverter has a short or one of the leg has shorted, you can directly put all your power to the other inverter. So that's why it relies like fault tolerant capability. So that's all the summary I can provide, and this whole work was supported by, of course, some of the major partners without which it would not be possible. So one is Ontario Tech University, and of course the group where I worked, that is Smart Transportation, Electrification, and Energy Research Group, which is called STEER, and it has been supported by our industrial and federal government partners, which is Canada Research Chair, DNV Electronics, Ford Motor Corporation, and CERC. So thank you guys. I'm open for the questions and your feedbacks.
Thank you, Dr. Rishi, for the very informative session on a very interesting topic, dual inverter drives for electric vehicles. We have very good response in the chat box, Rishi. So shall we read out questions one by one so that you can attend the questions, right, Rishi?
Yeah, sure. Can you just help me out from where I can do that?
Okay, then that's also, so please go to the chat window, Rishi.
Okay, chat.
There's an option like chat.
Or Eldo will also read out, Rishi.
Yeah, I will read out the questions.
Okay,
So,
no problem.
yeah, so first question. Is parallel operation of 2 or 3 voltage source inverter provided? I have PLL synchronization with one master and considering other inverter as slaves. If PLL sync is possible, and if it is done, can I control the power or implement load sharing using RS485 Modbus communication?
Okay, yeah, I took this chat. Okay, so it came from Dr. Chennagoda, I guess. Okay, it's parallel operation of 2 or 3 voltage source provided. I have PLL synchronizing with one master considering slave is possible, and if it is done, can I control the power and implement load sharing using RS485? Yes, I mean, you can do that. You can use RS485 or you can use a Modbus. I mean, not RS485 Modbus, but you have to use either one because one is serial and one is Ethernet. So yes, you can do that. PLL synchronization can be done. I haven't explored it by myself, but I personally believe it is possible.
Thank you, sir. Shall we move on to next question?
Yeah, so participant, okay, that's you, Aldo, I guess. How do you generate 2 isolated DC sources from a single battery source? So you have a same battery bed, right? You just isolate into 2, I mean, divide equally. For example, you have 1,000 cells. You divide it equally as 500. That's quite possible. Whatever you have battery bed, you divide it equally.
Thank you, sir. Next question.
During regeneration, what will be the modulation index? Good question. So regeneration. So regeneration means you have when you are having actually a mechanical input and your motor is freewheeling. Personally have not been explored, but I'm sorry, like I cannot give you a number, but it is possible. Maybe close. It can be put the value you want, how much power you actually want to dump on the battery. Please show scope and graph. It's possible to increase frequency. Please show scope and graph. It's possible. It's possible to increase frequency. I didn't get from Ujjwal Kumar.
I think he can explain the things.
Do I want to show my results? I'm not sure. Is it possible to increase the switching frequency? Is that the question is? Or is it possible to increase the operating frequency. Okay, I'll answer in short. Switching frequency, yes, you can increase the switching frequency. The reason for doing a lower, because most of the literatures have been done at particular 5 kilohertz and 3.5 kilohertz. That's the reason I chose that particular frequency. And yes, of course you can, but be careful when you are increasing the switching frequency, you have higher switching losses. But that can be taken off care of by new devices like GAN and all kind of latest devices. That's not for me, I guess. Recorded webinar will be available later. So, MATLAB simulation for better understanding in the graph. MATLAB simulation, I'm not obliged to provide that, but if you have, you can contact me directly if you have any questions, and we can have a separate session on that. I'll explain you. You can contact me. My mail ID was provided in my first slide. When either of the two sources is being used more, won't they face some of the drawbacks as the two-level inverters? Whenever you are operating at lower speed, you will have a two-level operation, and you have that losses of two-level inverter. But you are not always driving at lower speed. You'll have a speed increase also, right? I mean, the performance will be increasing when you have a multi-level operation. That means when you are driving at higher speed. But existing two-level inverters, you are always driving the lower speed and the higher speed at two-level operations. So that's obvious, right? Wow, can we use Kaplan filter for prediction in standard cycle? I really don't understand what does this mean, why it is required for a Kaplan filter, or what is the requirement of filter. I don't understand for standard cycle, and which is like driving cycle. I'm not sure. You can put me an email on more details if you want. Okay, next question is from Professor Pinky. Is there any chance of higher power sharing condition in inverter 2? Higher power sharing. Power sharing can be done. Power sharing limit is based on modulation index. So if your modulating wave is between the carrier bands, that is 0 to VDC, you can do the power sharing. But at modulation index 1, you cannot do any sharing, because that's touching, your modulating wave is actually touching the peaks of triangle carrier. I hope I answer your question, or maybe you can also contact me. When the bus clamping PWM issue, what was the switching frequency used for comparison? It was same 3.5 kilohertz. I know, because discontinuous has switching frequency different compared to this, so it was different. I don't remember right now the correct number, but the switching was different for bus clamp to make it actual optimal comparison to the triple and harmonic injected. It was different. It was average sense. It was different. I don't remember right now the correct number. Can we use supercapacitor for battery balancing in PWM? That's a good question. So that's one of the point which I wanted to share with you guys. Like when I've showed unbalanced capacity. So you can have a battery on one side and you can have a supercapacitor on the other side. So supercapacitors have higher capacities, right? So this can be utilized for a mass acceleration, for example, where you have a heavy load, for example, traction, where locomotives or buses. So at starting, to give the initial torque, you can have a higher capacity on one side of the inverter. So major power, or the instantaneous power, will be drawn from the supercapacitor side, and the batteries can be for maintaining the constant power. That's a good point by Nisarg. Yes, you can use supercapacitors on the other side. Feedback link, I don't know what does it mean. Which simulation platform did you use to work in open-ended? So Chandra, I have used MATLAB, PSIM, and Plex. MATLAB I have used for real-time simulator, and all the basic others general concept I have developed in PlexSim. I'm just wondering about the direction of flow current in the windings. Do you think diagonal-magnetizing reverse flow of current can be avoided during regenerative? I haven't personally explored it, but yeah, it is. I think it is possible, of course. What is the disadvantage of dual inverter power? The one, what I see right now, you have to use isolated DC sources. I mean, and you have to make a customized induction motor. Other than that, I don't see, compared to other multi-level topologies, this has any drawback because you have readily two-level inverters already available. Why more than 6 pulse is used in HVDC converter? Okay. HVDC, high voltage DC. I don't know if this is relevant to the subject which I covered, but can you please elaborate in your feedback what you meant by this, and I'll try to get back to you on this. Why can't diode bridge circuit be used in inverter? You mean NPC inverters? Diode bridge. I'm not sure about this. Sorry about that, analyst. Can a full wave bridge rectifier used as an inverter? Oh, I'm sorry, this is not at all possible because you are using a bridge rectifier, right? I mean, so can you use exchanging? I'm sorry. Hello.
So you can carry on.
Yeah. I mean decoupled control. Okay, yeah, decoupled control. Okay, I got you from Professor Pinky. So in decoupled control, yeah, whatever that 1 minus m divided by 2m, when you substitute the modulation index value in generalized form 0 to 1, that's the limit it can have. And yes, you are right, it can go above 1 also when you substitute the value. The graph you can see the graph. If you want, I can share you the literature work from one of the professor who has done that work, and in that you can see the modulation index can be made higher above 1, where you can actually pump more power to the battery charging also. Yes, you're right. Can we use finite set control, predictive control instead of PI control as there are no switch? Of course you can use. You can use I mean, model predictive control. You can use all fuzzy logic, whatever the latest controls you can have, and you can increase your switching states. But to let you know, industry always requires a standard to less complex standard. I mean, when you are researching something, when you are doing something, it eventually goes to a consumer, it eventually goes to a users. So always industry try to make it as minimum complex it can. Complex behavior, I mean, around the world nobody has time to research over it, but yeah, it is good for academics and it is good for researchers, of course. Yeah, can this topology be used for? Of course, it can be used. As I mentioned, it can be. This topology is used for any AC motors. I mean, most commonly it's used for induction motor as well as PMSM. Please share the mail details again. So my mail ID, you can take it down if I can write it down here. So it is rishi.menon@ieee.org. Okay, thank you, Janmay. Can we use rooftop solar panel to change one of the battery? Of course, you can. I mean, as I mentioned, this is just a proof of concept or a technology which you can use. The battery sources or the DC sources, you can have, as I mentioned before, similar battery sources. You can have battery sources and supercapacitor. You can have a fuel cell and a supercapacitor. Yeah, any combination you can provide. It will be difficult for PM to start up, I guess. Well, there are researchers. I can share you, or I can provide you the information on PM motor. I mean, dual inverter for PMSM is not a new technology, which is being still. I mean, the patent or the automobile industry, which they have provided, the decoupled discontinuous PWM has been done for PMSM motor, and I will let you know. Like it's done by GM, General Motors. Okay, thank you guys. Okay. All right. Thank you. Thank you, everyone.
Thank you, Dr. Rishi, for the
Thanks
very
a lot.
interesting topic and a very interesting presentation. And today we had very good response in our chat box. And we can see that from the chat box, most of the attendees were researchers and academicians who are really working in this field.
Yeah.
And yeah,
I know
because,
most of them. I know most of
yeah,
them.
yeah.
So yeah.
Yeah. In fact, we are very satisfied regarding the responses we received in the chat box, and we
Thank
can
you.
we really understand that your session was very fruitful. That is why that much responses came in the chat box.
Thank you. I'm
Once
honored.
again, thank you, Dr. Rishi, for sparing your
Yeah.
valuable time
Hello.
with us. Bijana madam, hello, Bijana madam.
Yeah.
Yeah. Please.
Yeah. Thank you, Dr. Rishi. In fact,
No
I got a
problem.
call. That's why I just had to stay away. So, but I can, like what Biju said, we have never seen such a great response in the chat window with so many questions.
All right. Thank you. Thank
So
you. Yeah.
that's overwhelming, right? In
Thank
fact,
you. Thank you.
yeah, especially because it's a very hot area where people are doing a lot of research, and once you get somebody whom you can ask your doubts, that's a great thing to happen.
Yeah,
Thank you
I
very much.
totally, yeah, thank you. I totally understand this session like remotely how it works, but as I mentioned, I am open to your feedbacks and your clarifications. You can mail me, or most of you have my numbers, I guess, so you can contact me directly also. So let you know. I mean, the electric vehicle researchers are, being widely done across the world. So we're like finding a right problem suitable to industry, what industry could be facing, it could be a challenge. So all the researchers, all the works should be concentrating onto that if you really wanted to work on electric vehicles, because let me tell you brief also, electric vehicles will never be researching on higher than 3 level for next in maybe 5 to 10 years, maybe in marine transportation, or maybe in locomotive transportation, you can have more than 3 levels, but for road applications, it is only up to 3 levels. So you can shoot me your doubts and your clarification if required. I can support as much as I can. Thank you so much.
Thank you, Rishi. Hope to meet you back in Kerala in some conferences.
Definitely. Hope this corona will subside by then. Thank you.
Yeah. Yes.
Yeah. And we welcome you to be back with us.
Okay, sure. Thank you, Professor Bijuna and Professor Biju. Thank you so much, guys. Thank you so much for your cooperation. Thank you.
Thank you all. Bye.